Okay. So I guess starting with some of the motivation behind the research I'm doing. If you look across many sectors of the economy, I think assembly lines are becoming increasingly complex, and the machinery used to manufacture things is becoming increasingly more expensive. For one extreme example, new circuit fabrications can cost billions of dollars to build these days. Um, and at the same time, one of the biggest drags on factory output is unplanned downtime, costing about 800 hours a year. For things like cars manufacturers, an unscheduled fault can cost about $50,000 per minute that the line has gone down. Um, and yet in 2017, there was a survey by GE that estimated only about 24% of manufacturers are using any sort of data-driven predictive maintenance to get ahead of these faults and potentially stop them before they become more serious. Um, this is despite the fact that sensors are rapidly becoming much cheaper and data becoming easier to acquire. Um, but some of the roadblocks, I think, to these automated fault detection systems becoming more widespread are firstly, they can require a lot of domain expertise to set up, both in the algorithms used for anomaly detection as well as the specific piece of hardware that's being monitored. Um, they can still require a lot of oversight from engineers and experts, and they can require large labeled data sets to train, which is particularly difficult in this case because ideally faults are relatively rare, and so getting large collections of recordings of faults can be very difficult. Which kind of brings me to the focus of my research, which is on online unsupervised fault detection systems. So the goal is to basically develop deep learning architectures that can continuously monitor incoming streams of sensor signals from a wide range of different types of sensors, kind of refine an internal model of how the system is supposed to behave when it's functioning normally, and then automatically kind of flag faults as they occur. Where kind of our key metrics are, we want it to be generalizable across a lot of applications. We want as high a detection accuracy as we can get. And then critically, we also want it to be very interpretable, providing diagnostic information to help speed up the repair process, as well as to quickly let engineers eliminate false positives so the machine doesn't become tedious to use. So to do this, I'm kind of framing the problem as just a more general case of anomaly detection for time series, where anomalies are kind of any points which deviate so significantly from other observations as to arouse suspicion. They're generated by a different mechanism. Um, and kind of the challenge in spotting anomalies in time series is that there are so many different types of them. There are some anomalies that you can just kind of pick out without any context from the rest of the signal. But there are many others that can be invisible unless you're looking at the correlations across all of the different sensor channels, across different points in time. You can get anomalies that are sudden if the machine breaks quickly, or can be caused by a slow drift in your system. Um, and the scale that they're visible on can vary by orders of magnitude. Um, in terms of general strategies for unsupervised anomaly detection, I think there are kind of three main families of approaches to attacking this problem. The first is forecasting, where your model learns to predict future values of your time series, and you look at the error in your predictions and turn that into a kind of anomaly score. The second is compression or dimensionality reduction, where you reduce the space of your input and then try to reconstruct the output and look at kind of how much error was lost in that process. And then the last one is kind of clustering or density estimation techniques. Um, and all of these kind of have different strengths and weaknesses regarding kind of the types of anomalies they can detect, how interpretable they are. Forecasting, for example, can be very prone to false positives in instances where your time series really is unpredictable. A classic example would be you don't know exactly when the machine is going to be turned on or off. And so because that's unpredictable, you'll see big spikes in your error every time that happens. And then in terms of like the features that you get and the interpretability, um, there's a lot of different strengths to each method. Um, but all of them fundamentally what you're trying to do is take this large multi-dimensional input and reduce it down to a single number representing kind of how anomalous or how off this time series seems to be. So that's kind of the main challenge of my project, is kind of combining all of these different methods into a single robust system that can work across a wide range of different types of problems. I'm going to come back and explain, I think, each section of this in more detail, but this is the architecture that I've been testing and kind of developing recently, the recurrent deep autoencoding Gaussian mixture model. It's built up of 3 different neural networks. The first is a autoencoder that does the compression step, kind of like a nonlinear form of PCA. The second is your estimation network, which predicts sample classes similarly to a Gaussian mixture model. And then the last is this recurrent unit in your latent state that lets the model see further back in time outside of the sliding window that you're compressing and kind of follow longer term trends. In terms of testing, I've been slowly building up a corpus of different fault detection tasks from different machinery. 3 I'll talk about in this project are with a data set that we collected from a plasma etcher, which had a huge suite of internal sensors, 40 different channels, everything from temperatures, pressures, everything else. The sampling rate was really low at only 2 hertz. And then for the wafers that were being etched, an electronic test was done on them at the end to see if the etch had been successful and the circuit was functioning as it should. And then the other 2 are a milling machine measuring tension, torsion, bending moments on the tool. Where here, the faults we're kind of looking for how new or worn the tool is. Because if your cutting tool becomes too worn, it can be prone to breaking. And the last one is our bearing data set, where we've got 3-axis vibration measurements from the bearing, sampled at incredibly high speeds, and faults were kind of intentionally induced by introducing tiny chips into either the ball bearings or the raceway. There. So going back to kind of each component of the network and demonstrating kind of how they work in isolation. For the compression network, if you take an autoencoder, which takes in a sliding window of your wide time series, you're training it to basically map that input to a much smaller space, which just has less hidden units in the center. And then you're training a decoder network to take that latent state and try to map it back out to your original high dimensional data set. You take the difference of those 2 vectors and you get your residuals vector, which is your error in reconstruction. And the residual vector kind of tells you how abnormal the current frame is, because over time your model should be learning to find the common factors of variation so it can make the most use out of this compressed space. And so whenever you see something unexpected, your residuals vectors will spike in magnitude. And then the latent state kind of gives you a compressed representation of your true system state that can be useful for many other purposes related to diagnostics.
Damien,
Using
before you keep going, can I just ask you a quick question about that? So maybe you're going to talk about this after, but where is the Gaussian mixture component that you mentioned in this in this structure?
Oh yeah, I'm gonna get to that afterwards.
Okay.
I'm kind of showing like how the pieces perform on their own, and then how you sort of string them all together.
Got it.
But yeah, so using just kind of a compressive autoencoder, we trained a convolutional architecture on 1,000 of these etching runs, testing them on an additional 200 runs, 100 of which failed and 100 of which are normal, and looking at the mean average error caused by compression. You can see on the right where all of the failed etches are in orange, all of the successful etches in blue, that you can already separate out a pretty significant number of the failed etches right off the bat. So then the second part, fault classification and diagnostics, is more about trying to provide meaningful information to help with repairs and let you quickly dismiss false positives. The problem with applying this directly to your time series is that clustering algorithms tend to perform really poorly in really high dimensional spaces. Um, but instead, clustering on the latent state from the autoencoder, you can get far more robust features. Um, so if you take GMM and train it in an unsupervised fashion using something like the Bayesian information criteria to figure out the correct number of classes, um, you can kind of get these really meaningful separation between different types of faults. We ran this on the Etcher database with no idea of what different types of faults were actually in that data set. We'd gotten it from another company with very little background information other than the labels that they provided, and came up with two different categories of fault, 0 and 5, it put them in. We had two classes that contained only normal runs, and then two other kind of borderline cases. Um, when you look at plots of which runs were in each category, in class 1, or the first fault class, here I've got it plotted in red, overlaid over a bunch of normal runs in blue. You could see that the valve seemed to be shutting off late, and that was ruining the etches. For all of the runs in the second fault class, the valve was acting normally, but the electrical temperature on one of the channels was reported as being significantly higher than we saw in the successful etches. So it did look like there really was a meaningful difference between these two types of faults in terms of what broke and what was ruining the etch. And you can kind of pick these most important channels out that are kind of most representative for each fault by looking at how high the residual is on each individual channel to categorize it. um, so the estimation network that we're using is effectively a way of combining the compression and clustering system into kind of one end-to-end trainable network. So instead of using expectation maximization to come up with your classes, instead what you're doing is you're taking kind of that same, what do we call it? The same metric that you're trying to optimize in Gaussian mixture models, the negative log likelihood, and using this as your loss function, and then training the weights of your estimation network by back propagation to get similar results. And then the last section, the recurrent cell, is basically to correct this massive deficiency in the model that outside of the sliding window, the model has no way to see any types of correlations that don't exist within a single frame, which means on data sets with extremely high sampling rates, you'll miss an enormous number of types of errors, and there's no way that you'll be able to detect model drift at all. And so adding a recurrent cell just to this last layer of your autoencoder kind of lets it also see how the state is drifting over time and pick up on these longer term correlations. So batching lots of different windows together and looking at how the state changes over time kind of increases your effective window size by another order of magnitude or two. Putting all this together and training this on our other two data sets, the recurrent version of our deep autoencoding Gaussian mixture model managed to separate out about 99% of the cutting runs with the milling machine. In blue are all of the runs with the new tool, and orange are all of the ones with the worn tool. And on our bearing data set, we got similar results where as soon as the defect was introduced into the bearings, you see this massive spike in your anomaly score. And so that's kind of where the project stands right now. We've got a reasonable number of positive results detecting different types of faults with a lot of different types of sensor signals, where the system was kind of trained without fine tuning between applications. and without any sorts of labels as to which runs were faulty and which ones weren't. And it also gives you a really rich representation in the form of the latent state, the errors on each residual channel, for kind of classifying different faults and kind of quickly figuring out what's going on with the machine. And the current thing we're working on now is kind of taking this system and testing it on more real world applications. For that, we're partnering with the clean room in building 39, where we've currently got an experiment ongoing where we set up a current and voltage meter to the LAM 590 plasma etcher in the back of their building, and have it streaming results to the cloud as different research groups use the machine. I think it's used for one of the classes on campus as well. And we're trying to answer two main questions with this experiment. The first is whether you can, whether it's possible to kind of detect faults just based off the power readings between the wall supply and the etching machine itself. And the second is, in terms of making fault detection systems more accessible to everyone, kind of trying to reduce the difficulty of retrofitting them in. When it comes to expensive manufacturing equipment, you often don't want to have to open up the machine, splice into wires to like attach new sensors into it. And so being able to like just monitor the power draw from outside the machine itself is like much less invasive. And that's where we are now. How am I doing on time?